Let's look at some examples of expanding a binomial using the binomial theorem. There's two variations here on the basic formula. One is where you've got a fairly low number here, and you can read off all of the coefficients from a fairly small display of Pascal's triangle. And it's just, Pascal's triangle has lots of interpretations and lots of meaning to it, but what we're thinking of is just each row of Pascal's triangle, like the fifth row here, is just all of the binomial coefficients in this expansion. So that doesn't mean, it means you don't really have to know where these come from, even though there's very cool counting interpretations of where those come from, and that's going to show up in the other kind of example. And you can just read them off the table. Okay, so we'll do an example like that in a second, where we modify these guys to make it a little more interesting. The other kind of example is where this is a relatively high number, and you don't want to just try and find some very complete version of Pascal's triangle, and you want to get it. You want to get it from scratch. And usually with those things, well, we can write this out in a somewhat more fancy way, that this summation can be tidied up into a sigma notation. And the powers of x, for example, we'll label this by k, go from 0 all the way up to 18. As they go up, the powers of y go down so that they always add to 18. And the coefficients are exactly just NCKs, and where n is just the total power. And in particular, what is often asked for is simply, what is the coefficient in front of one term here? Okay, so with that preamble, we'll do a couple of examples of those two different types. So like 2x minus 3y to the fourth. You could just expand that out by hand. It wouldn't be too grungy, but it's nice that Pascal tells you a good way to do that. So we're just going to write this down where the whole thing, 2x, that's what's in place of x in our formula. And here's a little bit of a tricky thing. The minus 3y is going to be the second part of the formula. So I'm going to write this as a 2x plus a minus 3y all to the fourth. And then I'm just going to say, okay, Pascal's triangle is 1 times this to the fourth. And I'm just going to do that part and not worry about expanding it out yet. Plus 4, that's the next thing in Pascal's triangle. I know I just erased it, but it's not too bad. Times 2x to the third times a minus 3y to the first. Plus 6 times 2x squared times minus 3y squared. Plus 4 times 2x to the 1 minus 3y cubed. And then plus a 1 times 2x, well, 2x to the 0, just like this didn't have a minus 3y at all, this doesn't really have a 2x to the 0, that's minus 3y to the fourth. And now I just tidy it up. 2 to the fourth is a 16, so it does not start with 1 because the 2 is contributing. Plus 4 times 8, 32, so it's minus 96 x cubed y. And this is a very common thing. When this is a minus, what we'll see is you get alternating signs, because sometimes these powers are odd and the minus sign lives. The next one, for example, the minus sign is going to die because it's a minus sign and squared. So let's see, 4 times 6 is 24, times 9 is 216. And then now minus, we got 8 times 27, and that's going to be same deal actually, right? Yeah, 216, as it happens. Okay, that's interesting. And that's going to be an xy cubed. And then the last one is a plus, that's minus sign to an even power, plus 81y fourth. Okay, it's really just a combination of the basic idea of a binomial expansion with the Pascal coefficients, which are really secretly NCKs or NCRs, or whatever you want to think about it, combinations, and then interacting with the extra coefficients that are coming from there. So that would be an example if they say, find the whole expansion, and it's a relatively small number, so we basically have those numbers memorized or just can read them off a convenient display of Pascal's triangle. Now, what if I had, let's say, let me just use different letters, 4p minus 5q, let's go back to that 18th power, for example. Okay. That would be a big thing to write out, okay? But what if I only want to know I want to know the p to the, let's say p to the 11, q to the 7 term. Okay, well, that term only is going to be an 18 choose, and you could get confused, theoretically, between, ooh, do I do 11 or do 7? The great thing is it doesn't matter. It's symmetrical. 11C11, 18C11 is the same as 18C7, so that's the one thing you can't get wrong, at least for that reason. Okay, times, okay, now I'm just going to take 4p to the 11th, and then the minus 5q to the 7th. Because that's the only way it's going to end up being some number that's going to come from this, this, and this, times p to the 11, q to the 7. Okay? And so that's going to be, now let's see, did I have that? 18, C11 is 31824. I've calculated that. You can get that off a calculator, for example. Times 4 to the 11th, times a minus, ooh, so that'll come out minus 5 to the 7th, times p to the 11th, q to the 7th. Okay. And then we could multiply that out to get a pretty gargantuan number if we wanted to, but I'm not going to worry about it. So that's another kind of this example where we just want a specific term, and we just go right to the particular term that's going on with that. The binomial coefficient times whatever that first thing is to the appropriate power times whatever the second thing is to the appropriate power to match what we want. One more example real quick. That's the basics. What if I had something where the powers were a little weird? What if I had like x squared, I'm going to make the coefficients a little easier. Let's say x squared plus 2y cubed to the, let's say 6th power. That's something we could do as a full expansion, but let me just do another one of that second type. I want the x to the, let me think for a second here. I claim there's an x to the 6th, y to the 9th term. Okay. That's interesting. 6 plus 9 is not equal to 6. Okay. Well, the deal here is that x to the 6th is x squared cubed, and y to the 9th is y cubed cubed. 3 plus 3 is equal to 6, so we really will get some term like this. Okay, so you just got to make sure that you're taking into account the fact that this is not just x, that's not just y. These powers are now, those exponents are now contributing to the overall exponents. Okay, so let's do it a little more carefully. Okay, what we're going to get, okay, we know we've identified these key numbers. That's really crucial. Okay, that's the k and the n minus k. So it's going to be 6 choose 3 times that thing, whatever it is, all of it, to the 3, times this thing, and I'm now going to include that 2. This is a plus now, so I'm not going to get a weird sign, but you could totally do it with a sign. Okay. Okay, so that, we're going to get blah, 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 plus blah, 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 blah. That's going to be one of the terms. It's actually going to be the middle term in the expansion when you take this thing to the 6th power. And it's because it's blah to the 3rd, and then 6 choose 3. Okay. All right, 6 choose 3. We could do that by hand. 6 times 5 times 4, just 3 numbers descending from 6, over 3 factorial, which happens to be 6, so that cancels. That's a 20. And again, if you're sitting in front of a display of Pascal's triangle, you see that the middle thing in the 6th row is 20. Okay. And my reminder is going off. Shush. Okay. And then x to the 6th. Ooh, and then 2 cubed. So that's an 8y to the 9th. So the whole thing is 8 times 20. It's 160. Okay. So that's the mystery thing. Yes, there is an x to the 6th, y to the 9th in this expansion, and its coefficient in front of it is 160. So those are a little bit trickier. And that's where I want to stop.